All right, we're going to dive into some rational functions today. So rational functions are those functions that have asymptotes that go horizontally, vertically, sometimes they're even slanted. But we have a process for how we're going to graph them, so I'm going to kind of take you guys through that process today with a few examples. And we are going to go step by step through these. These are the problems where you're going to factor the numerator, factor the denominator. You're going to look for things to simplify. That's when you have those holes pop up. You're going to look for your vertical asymptotes that come from your denominator. Your horizontal asymptotes come from comparing the numerator to the denominator. And then we're going to plug in some points and draw some curves. So that's kind of our 5-step process, and I was very general right there because we are going to go through some very specific examples. And I just want to note, it's the simplifying step. That's when you can find the holes on the graph. For example, if you had a factor of x that canceled on the top and the bottom, you'd know that you had a hole at an x value of 0. And I'm just noting that if the denominator is equal to 0, that's when you're going to find one of your vertical asymptotes. The horizontal asymptotes, we're going to break that down into a special case, case-by-case basis on the next slide. Let's go ahead and do that. So, okay, horizontal asymptotes. These are complicated because there's a lot going on. It depends on how the numerator compares to the denominator. Okay, so you have 3 cases, because either the numerator is bigger, it's smaller, or it is the same as the denominator. And when I talk about the comparison of the numerator and denominator, we're mostly talking about the degree on top and on the bottom, which means the largest exponent. So let's get into our individual cases. So case 1, the numerator's degree is less than the denominator's degree. Very simple. That means you have a horizontal asymptote at y equals 0. If the numerator is the same as the denominator, you're going to divide the coefficients from those terms. That's going to give you y equals some value. That's where your horizontal asymptote is going to be. If the numerator is greater than the denominator, that's when you're going to literally divide the numerator by the denominator. And whatever expression you get, that's an asymptote, but it's not necessarily horizontal. That case, that third case, does not pop up as often as the first two. So let's take a look at our first example here. We've got some sort of a rational function here. It looks like a pretty nice one that factors oh so nicely. I'm going to pull out a GCF on top, apply a little difference of 2 squares on the bottom. Don't mind my handwriting. It is not easy writing on this iPad. All right, so I've got a factor of x minus 2 on the top and the bottom, so I'm going to cancel that out. As soon as I cancel something out, I got to remember off to the side, that's where the hole is going to be. Let me just rewrite my simplified function. But yeah, I've got a hole that's going to occur at x is equal to 2. And I want to find the y value. I'm just going to plug 2 into the simplified function, which gives me 3/4. Ooh, that was a terrible 3. We'll go with it. So the hole occurs at 2, 3/4, and you can just use an open circle to plot the hole on the graph. Just make sure it's really clear and obvious that it's an open circle. We examine our denominator. We find a vertical asymptote to occur at x equals -2. Remember, the vertical asymptote is when the simplified rational function has a denominator equal to 0. We compare the degrees here. The numerator's degree is 0. The denominator is 1. So the numerator is less than the denominator. That means that the horizontal asymptote occurs at y equals 0. So I'm going to go ahead and graph my rational function. Don't mind my sketchy graph. I've got a vertical asymptote that occurs at -2. I've got a horizontal asymptote that occurs at y equals 0. I'm going to make sure that I emphasize that hole, that's a coordinate. It's 2, 3/4. I should probably put some tick marks on my graph. So 2, 3/4 is right about there. You guys are going to be using graph paper for these. And what I want to do is I want to test points on either side of the asymptote, right? So I know the asymptote is at -2, so I'm just going to try like -4, -3, -1, and 0. Just the nice x values that are kind of near that vertical asymptote. And I did the math for you, so those are the y values, and I can go ahead and I can start plotting those things. And there they are plotted. And hopefully I can make this look a little sketchy. Yeah, that's good. So there's my rational function. Usually they have those 2 distinct pieces. Usually they're opposite from each other. And just for this example, I want to at least write out the domain and range for this case. I'm going to use my interval notation that we've reviewed. Interval notation here, negative infinity to negative 2, negative 2 to infinity, not including the negative 2 because there is no point there. And the range, similarly, because of the asymptote, it doesn't include 0. Oof, that union symbol, really bad. Oof. So there's our first example of graphing a rational function. Let's do a little bit more of a fun one. This is one when we're not going to have that y equals 0, that nice case. We're going to have a same degree on the top and the bottom. And these do factor nicely. Note that I'm not going through the entire factoring process. If you recall, you split the middle, you find two numbers that multiply to AC that add to B. I'm not going through that whole process in this video. If you need to review factoring, do it on your own time. You guys should know how to factor by now. These do factor out, and the x plus 2's can cancel on the top and the bottom. Let me change colors. We're going to cancel them out with a little red pen. We got a hole. It's going to occur at negative 2 for an x value, and a y value of... I got 11 over 3. You guys might want to fact check me on that, but I think it's at 11 thirds. Remember, you can find the y value for the whole by plugging into the simplified function. So I've got my simplified function here. And now I got to find the vertical asymptotes. So we got a vertical asymptote at x equals negative 1/2 because that's when the denominator is 0. Because the degrees are the same, the horizontal asymptote happens at 3 over 2. That's because I'm dividing 3 by 2 from the numerator and the denominator. So I have the beginning pieces of this graph. So I'm going to start laying those down. We've got our vertical asymptote at negative 1/2. That, I think I hit negative 1/2. I might have missed. Horizontal asymptote at positive 3 over 2. And I want to make sure I include that hole. So the hole is at negative 2, and then I got to go up 11 thirds, which is like, what, 3 2/3? So I got to go up a little ways. Ooh, that's an open circle, guys. It's open. That's one of those ones, if you're taking a test, you like draw an arrow next to it, and you're like, it's open, I promise. All right, now we do need some points here. I can't use the negative 2 because that's where the hole is. I'm just noticing now how poorly I missed on the x value on that hole, but I don't really feel like changing it, so we're just going to kind of go with it. So these are the points that I decided upon testing. I'm not going to take you through that whole process, but you choose the x's, you plug them in. Now I've plotted those points on my graph. I'm taking note that that open circle is still there as well, that hole. Now if we look back at the numerator in our function, the 3x minus 5, setting that equal to 0 will give us our x-intercept on a rational function. So I end up with 5 thirds comma 0 as an x-intercept. That's just kind of a nice additional point that I can plot, which makes my graph a little bit nicer, even though mine was a little sketchy. Hoping that like somebody will get the sketchy joke, but that's fine. All right, so we've got our rational function. I would definitely draw an arrow next to that open circle because it is not obvious that it's open anymore. But hopefully that helped kind of overview the process of graphing rational functions.